tempted just to grab one out of the book. And you can actually mark, these drawings are scale drawings in the book. So what I'd like to do is let's go back here to something we've played with previously. As a matter of fact, you have a homework problem here, back on number 88, where you're doing relative velocity problems. And so watch this. You're going to like this. Here's a rigid body. I'll get down on my knees. Here's a rigid body pinned here at O. So you know A is going what direction? Down and to the left, perpendicular to this arm, right? Down here, perpendicular to this arm. So here's the velocity, and here's a known omega. And so here's a known velocity then. This is going to be 100 omega O. All right? Now, here's another rigid body over here pinned at C, and you know that its motion is, point B's motion is
to the left,
perpendicular to BC, right? Perpendicular to BC. So you know this point has to be traveling this way, to the left. Here's an answer that you were asking about earlier on number 88. Omega of BC here is 5.83 radians per second. And omega AB right here is 2.5 radians per second. Number 88. Okay, now, this is known over here. This guy's known, easy. The question is, what's the omega of this floating member, AB? What's the omega of the floating member, AB? Well, if this point A here we know its motions is in this direction shown right here, then that means perpendicular to it must be where the instantaneous center exists for this member. So it must be along this line somewhere. This point B on member AB is in motion to the left, shown here. So perpendicular to it must be a line of action. And so the coincident point of a perpendicular to the motion of the velocity of this point, the coincident point with that line, and the line over here is where the instantaneous center exists. Now I'm going to push this up a little bit, and here's where the instantaneous center exists for member AB. You can work the geometry out on this problem by knowing these geometric links. You can figure out this geometric location. And then all you have to do would be to take, watch this, you can take this velocity then, 100 omega O, and that must be equal to, that speed, that velocity right here of this point must be equal to this lever arm, let's call it L, must be equal to L times the omega of member AB. So the omega of AB is going to be 100 omega O, omega naught, divided by length L. That is geometry, simple geometry. Here's another homework problem you have. Now, back here in this section, though, you were supposed to do these by vectors. You're supposed to do these by vectors. So make sure you do them by vectors, but you can use this instantaneous center to very easily check and see if you got your work right. Look at this member right here. in this mechanism where you have a known velocity up here. A known velocity up here. That means this point is traveling straight downward. And this point right here at B is on this colored member. So the instantaneous center must exist where? If this point on this colored member is moving straight down, then the instantaneous center for the colored member must lie where? Where?
Yeah, with the color member can be rotating about B.
Oh yeah. Well, no, it's not. Well, it's rotating. Yeah, it is rotating about B. Huh? It has to be perpendicular to that velocity, doesn't it? Doesn't the instantaneous center of the colored member have to be perpendicular to this velocity, known velocity? Okay. Across here. Has to be out along there somewhere. And then, what do you know about the motion here of A? Oh, well, it has to be, the motion is horizontal, right? Because this is getting pushed down, it's causing this thing to kick to the right, right? So then the instantaneous center once again must be along what line from this point?
Perpendicular to the...
Perpendicular to this velocity. So it has to be, right there. So here's the IC for this member ABC. The question I believe asked of you here in this homework problem is, what's the velocity of this point out here? Well, check that out. It has to be perpendicular from the IC. You're still on that member. You go over here, and it's got to be perpendicular to this lever arm here. So if you geometrically can figure out where that location is, and you know the velocity of this point, you divide this velocity reading by this length. That's going to give you the omega of this colored member, and then you're going to take that omega and multiply it by this length to get the velocity of this point C over here. Simple geometry to do that. Let's back up a little further. Look at this one in the book. This problem gives us the triangular plate's angular velocity is given to us as 3 radians per second clockwise for the colored plate. For that instant, determine the angular velocity of member BC over here. So, we want to get we know something about this plate. Here it is. Okay? So, what do we know about the motion of A, given this geometry? Its velocity is up or down? Plate here is rotating clockwise. So it's causing this point A to lift up. It's actually not too important that you know that. Okay? But it's along this line. So the IC has to then be, so the velocity of A has to be this way, but along this line, and perpendicular to it is going to be the IC of the plate. And then this plate, the colored plate, this point is moving what way?
It has to be parallel to the number.
Pinned at C, that means it has to be moving horizontally, right? So the velocity of B. So again, on the colored plate now, where's the IC? It happens to be down here at C. So this is the IC for the colored plate, which happens to be ABD. Okay. So if this is the IC, and you know that that plate is moving with an omega of 3 radians per second,
You know the radius from C to B? So
Yeah, and so then you can figure out the velocity of B, or the velocity of A, or the velocity of D. See, the velocity of D is going to be three times this lever arm. Okay. So anyway, you can use this as a handy tool. There were 3 short problems assigned in the next section, which is the section addressing the instantaneous center. Let me look in my book, see if there's anything there that I should show you additionally before we look at acceleration. I think that's probably adequate on that. We have about 15 minutes left. I passed out one handout to you so far, I believe, which is a problem on page 391. Okay, so this is the problem out of the text. Page 391, number 148. And I gave you a detailed vector solution of this. Now what I'm trying today is to see if me doing things on the overhead here, if that's coming across to you or if I'm losing you or not. Am I losing you or not? A little bit harder to follow than doing it up here. Okay, yeah. So I think what we'll do is let's go ahead and look at the acceleration. The first page of the solution I handed out to you is the velocity portion of the problem. So what you have to do, I'm going to come back up to the board, is what you have to do with a mechanism is you oftentimes have to work out the velocity problem first. Because it should make sense to you that you need to know the velocity, the omegas, before you can then do the acceleration problem. Does that make sense? Because in our equation, our governing equations here, we have our velocity of A is equal to the velocity of B plus the velocity of A relative to B, where this last term is an omega cross R. And you should be getting almost automatic on that. When you take the derivative of this, when you do your velocity problem and you figure out the omegas in your mechanism, so you get the omegas, okay, from this problem. Then you develop the acceleration. You develop the acceleration. And that's going to involve terms similar to this, involving those omegas that you found. And B and A may have some omegas associated with them, like we saw in the last problem or so that we've done. Okay, so these guys might have some omegas associated with them as well. And don't forget, there's another term possible here, an alpha cross R of A relative to B. Okay, so here's the governing equation for the acceleration on a rigid body between 2 points on a rigid body. Okay. So the first page of the handout I gave you did the velocity problem in detail by a vector approach. And we have the mechanism shown up there, and I'll draw it on the board here. We have CBD CBD, and it's hooked onto member AB, and this is pinned over here, I believe. Yep, no, it's a pin. And then the support point is halfway in between these 2 points. Like that. What's given here, and this is point O and A. Here's O and A, and these were 100 millimeter regions. Okay. So this is 1/10 of a meter, 1/10 of a meter, and then from the geometry, this is 15/100ths of a meter, and 75/1000ths of a meter. Up to there, and this turns out to be 1/4 meter. And the given information in the problem has an omega of 40. Which way is that heading? Up, yeah. So this member was given to us, the omega of AB, as 40 radians per second. When you do the velocity problem, work it out, the omega of BC turns out to be 40 radians per second also, just by coincidence of the geometry. And it's positive, so that means this member is rotating counterclockwise as well. And then member OA down here is a plus 80, and so it's rotating counterclockwise as well. So omega OA is 80 radians per second. So as I was saying, you have to do the velocity problem first to get these before you start the acceleration problem. Okay. So page 2. You don't need to take notes because I provided it for you. The acceleration of point B is equal to the acceleration of point A plus the acceleration of B relative to A. Now this starts to get a little bit involved. So what we end up having here is, I'll start over here on the left, is the acceleration of B is going to be alpha of member BC, unknown value, k hat. We have to cross that for member BC. We have to cross that with R of what I'm trying to get right here is acceleration of point B. So then I have to cross it with R of B relative to C, which happens to be 0.15 J. Is that all right with people? That's the acceleration, that's the tangential acceleration, the R alpha type of term right there. That's what this is. And we have to add to it the fact that B is rotating about C. What other part of acceleration exists for B? Acceleration of B. Has to be one pointing back towards the rotation point, doesn't there? And that's the omega cross R. So that's going to be the computed value, which is 0.15 lever arm, and the omega BC is 40. So its magnitude is what? What's the magnitude of the normal acceleration pointing back downward here? its magnitude is this r omega squared, isn't it? The r omega squared magnitude, and it's pointing straight down. Isn't that quicker than doing an omega cross r calculation for that point? Much easier. So once you know this omega, go ahead and draw the fact that you know that you're going to have a potential tangential acceleration of this point about its root, right? And the other one has to be pointing back towards its rotation center. So its magnitude, as I wrote there on the paper, is a negative 0.15 lever arm, r, and it's 40 squared k hat. I'm sorry, j hat. That's going to be easier for you than doing an omega cross r on that. And so that takes care of that side. You come over to the other side, and we now have to write the acceleration of A. A is over here, rotating about O. So it similarly has the potential for an R alpha here too, doesn't it? And what else? You still awake? What else?
And also normal acceleration
pointing back towards here, right? An R omega squared type of term pointing back towards O. So what I'm going to do is I'm simply going to write R of OA, which actually happens to be a length of 0.1, right? Times an unknown alpha of member OA. And that acceleration, R alpha, has to be pointing upward, J. The normal, the potential R omega squared, has to be pointing back towards O. So I'm going to assign a negative I to it, and so it's going to be a lever arm 0.1, and the omega on that member was calculated earlier as 80 squared. There's your R omega squared, and it's in the negative I direction. So here's your acceleration due to A. Okay? I'm trying to save you a little bit of extra effort, because otherwise you'll have to be doing a cross product here, an alpha cross R, and here an omega cross R. But you don't have to do that on these ones that you know the fixed axis rotation on, like this point C, acceleration of B, and similarly the acceleration of A being about 0.0. Okay. Yeah, they work out nicely. And notice how important it was to have that information about the velocities, the omegas from earlier. Okay. Where it gets a little stickier now is this guy. The acceleration of B relative to A. B relative to A. And that's, again, that potential circular motion type of thing about point A. Okay. So what we have happening there, I've written the detail out. I think what I'm going to do is I'm just going to put that up on the overhead briefly in the interest of time. And I've written out a bunch of detail here that you'll find hopefully helpful. And I'm going to back off on the telephoto a little bit here so you can sort of see that detail. So here's the terms we were just discussing right in here and here. And then this is the acceleration of A or B relative to A. Here's the alpha cross R plus the normal acceleration and that member's omega was that, and the R, so it's a quarter of 1600, So its magnitude is r omega squared, looking at that member. So this is the magnitude of the r omega squared, and here is a unit vector, a nice little unit vector describing the direction from A to B. Oh, actually, I'm sorry. Be careful. This normal acceleration has to point from B back towards A. So that's why I have a positive I component here and a negative J component. Okay? So what I'm going to do on Thursday, or actually, this is Thursday. What we'll do next Tuesday is we'll spend more time on this acceleration issue. And you can use this problem, though, with all the detail to study it, and that'll help you doing some of the acceleration problems that have been assigned. Okay, so we'll see you next Monday over at the Math Resource Center at 4 o'clock. Don't forget to bring the homework with you. Okay.